at 90%. And when the aircraft decelerates to approximately 170 knots, push over to half G until reaching an appropriate recovery airspeed of 175 to 200 knots. Start this maneuver low enough in your area to prevent flying out of the top of your area. Also, don't exceed the oil system limitations. The first time you demo this maneuver, it may cause some anxiety in your student. The student will get light in the seat, and the airspeed may decrease until it no longer registers, and the aircraft will be extremely sluggish to control inputs. Once exposed to this maneuver, the student will realize that the aircraft has inherent positive aerodynamic stability and will not depart controlled flight even at very low airspeed. AOA stalls an aircraft, not airspeed. Emphasize to your student that the stability maneuver is not the standard procedure for recovering from a nose-high attitude. However, it can be used to recover from extreme nose-high, low airspeed situations. Be sure to caution your student to avoid abrupt control inputs during the stability demonstration. Hard turns get the student used to maneuvering the aircraft at high airspeeds and G loads. One technique is to accelerate to 350 to 400 knots with a power set at military. Roll to 90 degrees of bank, load up to 4 Gs, and hold the turn for approximately 45 degrees and reverse the direction of turn using coordinated aileron and rudder while maintaining a constant 4 Gs. Perform the rolls using a variety of control inputs: rudder only, ailerons only, and a blend of the two. Make note of the airspeed after each turn reversal. A slight descent will probably be necessary to conserve the airspeed. Be sure to guard the stick while the student is performing hard turns. The aircraft is operating well within the G overshoot range, very close to the unsymmetric structural limits. The student should learn that hard turns are more than yanking and banking. The student should now understand that coordinated flight control inputs, rudder and ailerons, are most effective in rolling the aircraft at high G loading. Operating within the G overshoot range of 0.8 to 0.95 Mach requires caution and finesse to avoid exceeding the structural limits of the aircraft. One final warning: caution your student not to pulse the stick while performing hard turns. Even if you're guarding the stick, the likelihood of a G overshoot is great. The final characteristic maneuver is the acceleration maneuver. The intent of this maneuver is to teach the effectiveness of 0 G during aircraft acceleration. A common technique used to demonstrate this is to start the maneuver at 300 knots, accelerate to 400 knots using military power, and 0 G. Note the time and altitude required to accelerate to 400 knots. Keep the oil gauges in your cross-check and don't exceed the oil system limits. Now, re-accomplish the maneuver, except maintain 1 G on the aircraft. Note the time and altitude difference for acceleration. The maneuver can be performed in a bank. This maneuver should convince the student that the aircraft accelerates best in a 0 G nose-low high-power setting scenario. The aircraft has minimum induced drag at 0 G. We've presented a lot of material. Time for a brief review. Your rudder effectiveness demonstration should have taught that at high angles of attack, the rudder is quite effective in rolling the aircraft. That at low angles of attack, the rudder is not as effective in rolling the aircraft. The low-speed aileron roll will show that the ailerons are very effective in rolling the aircraft at low angles of attack. That the ailerons are not as effective in rolling the aircraft at high angles of attack. The stability maneuver will demonstrate that the aircraft has inherent positive aerodynamic stability and will not depart controlled flight even at very low airspeeds. That AOA stalls the aircraft, not airspeed. After performing hard turns, recognize that coordinated flight control inputs are most effective in rolling the aircraft at high G loading. Operating within the G overshoot range of 0.8 to 0.95 Mach requires caution and finesse to avoid exceeding the structural limits of the aircraft. The importance of developing a feel for varied G loadings while clearing in the direction of the turn. Finally, the acceleration maneuver should demonstrate that the aircraft accelerates best in a zero-G high-power setting scenario. The aircraft has minimum induced drag at zero-G. Well, that's about it.
This program discusses how to land the T-38 in both normal and no-flap configurations and how to handle some landing irregularities. The landing phase begins with power reduction and ends with your wheels touching down in the flare. This program will not show you how to fly the traffic pattern, but begins with the landing phase itself.
In order to understand the landing phase better, we've broken it down into three distinctive parts: the power reduction, the round out, and the flare. When you are on a normal glide path, you're flying on a 3.5 to 4 degree glide path and have a descent rate of 350 to 400 feet per mile. If you're flying the proper airspeed for your fuel weight and configuration, you'll have a green donut in the AOA indicator.
On this glide path, the T-38 is already in a partial landing attitude, and if you did nothing, you'd hit very hard right on top of your aim point. Since we'd like to use the airplane again, you'll need to reduce the descent rate to make a soft touchdown and slow down so you'll be able to stop on the concrete available. The purpose of the power reduction phase is primarily to slow the aircraft down. Exactly where to start reducing your power depends on how fast you retard the throttles, your height above the runway, your sink rate, wind conditions, and whether you are fast or slow compared to your computed final approach airspeed. Your goal for most landings is to arrive over the threshold approximately 10 knots below the final approach speed. The power reduction point for most patterns will be about 1,000 feet away from the threshold, or at many Air Force bases over the beginning of the overrun. A smooth power reduction means just that. Smoothly pull the throttles back. Don't just chop them to idle when you're flying over the overrun.
The round-out phase decreases the descent rate of the airplane to an acceptable rate for a smooth touchdown. Pitch and power changes will result in the aircraft transitioning from what appears to be a descent to what almost appears to be slow flight a foot or two above the runway. In order to get to this point, you'll increase backstick pressure at a rate to increase your pitch attitude as your airspeed decreases. This can be kind of tricky at first, but you'll get it with practice. If you pull on the stick too rapidly, you'll find that the aircraft will climb. If you don't pull enough, you'll land prematurely. In the final phase of landing, the flare, the airplane will touch down. During the flare, the control inputs will result in the nose of the aircraft coming up even more than the slow flight attitude at the end of the roundout, but the aircraft will actually descend the remaining few feet to the runway because of thrust efficiency for the flight condition. The rate of backstick pressure is critical because if you pull too much too soon, you'll climb, which is undesirable during the slow descent of the flare. On a full-stop landing, continue to increase back pressure after touchdown to aerobrake without becoming airborne.
For a touch-and-go landing, lower the nose to takeoff attitude and smoothly advance the power to mill. Now let's look at the landing phases for normal and no-flap landings. We'll assume a UPT-type runway with an overrun of about 1,000 feet. Also, calm winds are used for the following discussion. For a normal full-flap landing, the power reduction begins as the nose of the aircraft enters the overrun. You have the flap slab interconnect system working for you with flaps down, so the back pressure to begin the roundout should occur a full second after the beginning of the power reduction. Continue flying the aircraft toward the threshold with the intent to cross the threshold about 3 feet in the air, 10 knots below approach speed with a very slight sink rate. This is the point where the flare begins and is where you should begin shifting your eyes down the runway to get a broader perspective of your height, drift, and sink. Continue applying backstick pressure as the aircraft slows down. Touchdown should occur about the time you reach 130 knots plus fuel. For a no-flap landing, the power reduction begins just before the nose of the aircraft enters the overrun. Because you are flying a higher true airspeed than on a full-flap approach, you need to reduce power early. The jet will cover the distance of the overrun faster, so to cross the threshold 10 knots below final approach speed, begin reducing the power earlier. Unlike the full flap landing, the round-out begins simultaneously with the power reduction on a no flap. This is because the AOA change needed to produce the required lift is greater on a no flap than on a full flap. Also, the slab movement per inch of stick travel is less on a no flap because the flap-slab interconnect system is not in effect. For these reasons, the back pressure to begin the round-out should happen at the same time the power reduction is made. The objective is the same, to fly the aircraft to a position over the threshold about 3 feet in the air with very little sink rate and about 10 knots below approach speed. Remember, the distance the stick will travel to get to this point is greater than on a normal full flap landing, so be prepared.
Like the full flap, the flare begins at about the threshold with ever-increasing back pressure to slow the aircraft down to a touchdown at 145 knots plus fuel. Don't forget to shift your eyes down the runway to get the big picture of what's happening with the landing. A quick word about the single-engine landing. You're in a thrust-critical situation, so maintaining a minimum of final approach speed until the power reduction is made is very important. There's nothing unusual about the landing itself. Just treat it like a normal full-flap landing. When landing with a headwind or tailwind, there's one main adjustment you need to make, and that is when you begin the power reduction. A headwind means you'll be spending more time over the overrun because of your lower ground speed, so you need to delay the power reduction a second or more depending on how much headwind is present. If you're landing with a tailwind, you need to start the power reduction a bit sooner because your higher ground speed means you'll spend less time crossing the overrun, so you need to begin slowing sooner. Now, how much sooner or later you start the power reduction depends on how much wind is present. As a technique, use about a second for each 10 knots of headwind or tailwind that you have.
The final topics we'll discuss in this program are landing irregularities. Landing irregularities are caused by not applying the proper control inputs for the required flight situation. Since you've caused the irregularity, you're the one who must know how to get out of it. A good rule of thumb to follow throughout your entire flying career is, if things don't look right or feel right, go around. The most severe landing irregularities are the balloon, bounce, excessive sink, and over-rotation. The balloon is a result of over-rotation of the nose of the aircraft. It may occur because of an abrupt round-out or an abrupt flare. Notice the key word here is abrupt. That means too fast a rate of back pressure in relation to the airspeed. That's why the aircraft climbs, or at least levels off, when you're trying to land. You have too much airspeed to raise the nose that quickly. The correction needed for a balloon is to relax the backstick pressure so you can sink back to the runway, then reestablish the landing attitude until touchdown. The bounce is also caused by not flying the nose of the aircraft properly. It's kind of like a rock skipping across the water. Because of an incomplete flare or hard landing, the aircraft hits the runway, then bounces back into the air until it settles down again. For a bounce, all that is normally needed is to reestablish the landing attitude until touchdown. For large or pronounced deviations, perform a go-around immediately. Push the throttles to mill or max power as necessary, lower the nose to a safe pitch attitude, and go around and try again. Excessive sink can occur anywhere in the traffic pattern, but on short final is one of the worst places to let it happen. An excessive sink rate is not always characterized by heavy buffeting and a red chevron in your face. It can also happen on a fast final approach with a lower than normal pitch attitude. A good example of this is when you're correcting for an excessive steep final and you've got your engines in idle trying not to gain any airspeed. Once you've recognized that you've got an excessive sink, execute a stall recovery and maximum afterburner, disregarding published ground track. The over-rotation occurs just like the balloon, but where it occurs makes it different. Over-rotation normally happens during the initial or touch-and-go takeoffs. It's caused by too much back pressure for the airspeed and results in premature liftoff, buffet, and low airspeed. To correct this situation, let the aircraft accelerate, and once you have things under control, take off. Landing the T-38 is challenging and rewarding, and like so many other aspects of flying, if you keep the basics in mind and apply them with good judgment, you'll achieve consistency and ultimately excellence.
Techniques by analyzing your own performance through continuation training or informal discussions with other instructors. This program includes some of the more widely accepted techniques. Many other accepted techniques may be found in the T-38 Instructor Techniques handout. The landing phase actually begins on initial. Some things need to get done here to ensure a properly executed landing occurs. The student needs to plan the pattern before the break. Get the checks and airspeed computations done early. With a new student, you have to set the pace and establish good habit patterns. Runway alignment is important. Don't allow the student to overshoot initial and insist that the student maintain runway center line. Also on initial, ask the student to analyze the winds. One technique is to set the heading marker on the wind direction called by the RSU. This will provide a visual aid of the wind vector for the surface winds. You can analyze the pattern winds by pointing out the crab angle required to maintain runway alignment. Also, listen to the RSU for gusty winds or crosswind landing procedures. Clear for other traffic. One technique is to have the student start at takeoff leg, track up through the closed pull-up crosswind area, and follow the inside downwind track to the perch. Emphasize clearing with the eyes and ears. Your students must know if someone's on the closed downwind or if there's a straight in. They'll know this by listening to the radio, but don't let them rely solely on this. They must also visually clear. One last comment. I know this sounds obvious, but don't rely on the student to clear. You must also clear. You must always mentally fly your aircraft as if you were on the controls. At 2 or 3 miles out, choose a ground reference for the visual break point in the direction of the break. Plan for the winds and traffic in the pattern. Break at the predetermined point. Clear one more time before you go. Crisply roll to approximately 60 degrees of bank, reduce the power slightly, about a knob width, and pull. One technique is to have the student maintain a constant back pressure and use slight bank changes to correct for minor altitude deviations. As the airspeed decreases, you'll have to increase the pitch slightly to maintain level flight. Add nose-up trim through the brake so as to be trimmed up on downwind at or below 240 knots. Once established on inside downwind, the student should be thinking of clearing, spacing behind other aircraft, crab angle, which is about twice what you had on initial, trim, and configuring. A good technique is to maintain at least 220 knots prior to configuring. A common student error is to accelerate above 240 knots and then not be able to configure at the normal point. Guard the gear handle to prevent overspeeding the gear. Now that's important, so let's say it one more time. Guard the gear handle to prevent overspeeding the gear. Configure a beam the touchdown point with gear and flaps as required. There's a tendency to climb as the flaps extend. Pre-brief your students on this so they expect it and are ready to correct. Now, demand a visual and verbal gear configuration check. The student should check gear handle down, light out in the handle, 3 green indicator lights, flap set, and hydraulic pressure up. Confirm the configuration and the before landing checklist is complete. Never let the student roll off the perch with an improper configuration. Break out if necessary. The power may have to increase slightly after configuring. Some IPs hold 200 knots to the perch. Others hold final turn airspeed. Whatever your techniques, don't allow the student to get below final turn airspeed. While there may be ground references that identify the perch, the runway is the primary reference. One technique for determining the perch is to look over your shoulder and look down the first chevron in the overrun. A common error is rolling off the perch late. Don't let this happen. Either ensure your student rolls off at the correct spot or direct a breakout. Clearing is ongoing throughout the pattern, so at the perch, clear for the final turn in front of you. Look for any possible straight ends or the wide, long, no-flap pattern. Look and listen. Aircraft are likely to be any place. Recheck the configuration and make the gear down radio call. On the roll in, use the full 45 degrees of bank and set the picture. The common picture you hear discussed is 2/3 ground and 1/3 sky. To be more exact, the student should see the horizon intersecting the corner of the glare shield and the canopy bow at a 45-degree angle. They'll be able to estimate 45 degrees by using the horizon as a reference. One common error is to roll in, not lower the nose, and add back pressure, resulting in a level final turn. Emphasize the picture first, then refine the pattern with a rapid cross-check of outside and inside references. It's essential that the student blend in back pressure to get the turn going. Delaying the back pressure and then not trimming may cause an overshot final. Because of the increased angle of attack, you'll have to increase the power to maintain final turn airspeed. It takes about 85 to 90% power in a normal final turn, depending on gross weight and configuration. You have to monitor the pitch attitude, airspeed, and AOA closely during the final turn. Always be ready to assume aircraft control. Wherever you place your hands in the pattern, they should not be far from the controls. Be careful not to ride the controls or make unannounced control inputs. If the final turn was started correctly, the turn itself is nothing more than monitoring progress with minor pitch, bank, and power changes. Teach your student to trim throughout the final turn. You can detect improper trim by erratic pulsating stick inputs. Establish the habit pattern of cross-checking runway, AOA, and airspeed about every 2 seconds. Halfway around the final turn is a good place to check your progress. In the pre-brief, you told your student what parameters to look for at the halfway point. They should have lost about 1/3 of the pattern altitude by this point, or approximately 1/2 of the altitude to your rollout altitude. A technique for consistently rolling out aligned on final is to mentally extend the runway center line. This should help